Welcome everybody to another edition of the Heidelberg Joint Astronomy Colloquium. Last week we heard about supermassive black holes, how they were influencing evolution of very distant galaxies. Now we're sort of, excuse the pun, but we're zooming right back in to the Milky Way. And we'll hear about lower mass black holes, but in some respects no less mysterious. And I'll ask Ralph Klesson to introduce our speaker, Michela.
Yes, thanks. So with great pleasure, I introduce Michela Mapelli to give today's colloquium. Michela is quite a distinguished scientist. She got her PhD in 2006 from CISA in Italy, and right for her PhD thesis, she got two distinguished prizes. That is the Graton Prize and the Tacchini Prize from the Italian Astronomical Society for the best PhD thesis in Italy in astronomy and astrophysics. Her first postdoc took her to the University of Milano and, to Zurich, to the Institute for Theoretical Physics, where she got a Forschungskredit from the Swiss National Fund that ended in 2009. And then she came as postdoctoral fellow back to Italy to the University of Milano. Since 2011, she is permanent research staff at INAF. There was a period of time that she was interims professor, full professor and chair of the extragalactic group at the Institute for Astrophysics and Particle Physics in Innsbruck in Austria. And since 2018, she is back to Italy and works now at the University of Padova in the Department of Physics and Astronomy. So she, as I already mentioned, got a couple of very distinguished prizes and awards. In 2015, for instance, the Marak Prize for the best early career research in theoretical astrophysics. And in 2017, she got awarded a ESC Consolidator grant on investigating the demography of black hole binaries in the area of gravitational wave astronomy. And this is also the topic of today's colloquium. And with that, let us give a warm welcome to Michela. So, please.
Yeah, thank you very much, Richard and Ralph, for this very nice introduction. And thanks everybody for being here. It's really a great pleasure for me to be virtually here with you. And thanks for the invitation. So let's talk about binary black holes. I will first briefly summarize a few observational facts from gravitational waves, and then I will focus on the mass of black holes and on the formation channels of binary black holes. In 2015, the LIGO interferometers obtained the first direct detection of gravitational waves. And after this first result, LIGO and then Virgo in Italy, which joined in 2017, obtained many other observations, many other results. Currently, we know about 50 binary compact object mergers from gravitational waves. Most of them are binary black holes. And the data from the last part of the third observing run, the last observing run of the LIGO-Virgo-KAGRA collaboration are still being analyzed. So I'm pretty sure there will be new data, new detection quite soon. And one of the key information that we can derive from these observations is the mass of the binary compact objects. At the beginning of my talks, I like to show this plot because it's a very nice summary of the masses of neutron stars and black holes for which we have a good mass measurement. These are not just gravitational wave events. There are also electromagnetic observations. But the orange dots here are the LIGO-Virgo binary black holes, so the gravitational wave black holes, while the green dots that I highlighted here are also black holes, but black holes in nearby X-ray binaries, for which we have a dynamical mass measurement. And you see quite clearly that the maximum mass of the green dots is about 20 solar masses, while a large portion of the orange dots are above 20 solar masses. And this was quite a surprise for the astrophysics community that LIGO and Virgo observed black holes with mass of 30, 40 solar masses. And now we even have this event here, 1905-21, which is way more massive than the other ones. And I highlighted here other two events that are peculiar, 1904-12 and 1908-14. They are peculiar in the sense that they have a quite low mass ratio, much lower than 1, while the bulk of the LIGO-Virgo-KAGRA black holes are nearly equal mass systems. They are consistent with equal mass system. And I will discuss in a few slides why this mass ratio could be a key to interpret their formation. 1908-14 is very peculiar also for the secondary component, which has a mass of about 2.6 solar masses. This is either the lightest black hole or the heaviest neutron star we ever observed. And then there is 1905-21. To understand its impact for astrophysics, I will shortly define what an intermediate mass black hole is. It's a black hole with mass between 100 solar masses and about 10 to the 5 solar masses. And below 100 solar masses, we have a lot of observations from X-rays, from gravitational waves, from microlensing. Above a few times 10 to the 5 solar masses, we observe supermassive black holes at the center of galaxies. But in this intermediate mass regime, we have very few strong candidates from electromagnetic observations. And now we have 1905-21 merger product, merger remnant, which has a mass of about 140 solar masses. And this is not the only peculiar aspect of the system. This system also shows support for components of the spins that lie in the orbital plane of the binary. They are not aligned with the orbital angular momentum, and this has also impact on the interpretation of this event, as we will discuss. And the primary mass is about 85-90 solar masses, which is in basically a forbidden region from theory, as we will discuss in a few minutes. So let's now see from a theoretical perspective, how can we understand the mass spectrum of stellar-born black holes? What we know, what are the physical processes that affect this mass spectrum? And first of all, the first key aspect is the mass evolution of the progenitor star. We know that massive stars do not evolve at a constant mass. They lose mass during their life by a process called stellar winds. And for massive hot stars, which are black hole progenitors, these stellar winds are line-driven stellar winds, which implies that they depend on the stellar metallicity and on the luminosity. And in particular, the lower the metallicity is, the lower the mass loss rate, the higher the luminosity is, the closer it gets to its Eddington value, to its Eddington limit, the higher the mass loss rate. And one of the simplest models that we can use to describe this double dependence is this one. We describe the mass loss rate, m dot, as a function of the metallicity, capital Z, to an index alpha, which is not constant, but it depends on this factor here, gamma, which is the ratio between the luminosity of the star and its Eddington value, its maximum equilibrium value. And if we fold this model for stellar winds into a stellar evolution model, we can describe the evolution of a massive star like this. So here we start from an initial mass of 90 solar masses, very massive star, and we evolve it with different metallicities. This one, the red line, is the solar metallicity, is pretty high. And these are lower and lower metallicity. And we see that the metal-rich stars lose about 2/3 of their mass during their life, while the metal-poor one retain most of their mass. And this rightmost point here of each line is basically the final mass of a star, the mass at the onset of core collapse. Which leads us to the second crucial ingredient, which is the final fate of the progenitor star, core collapse, supernova, or direct collapse. Here, the fundamental question is, does a star explode at the end of its life as a core collapse supernova? If the answer is yes, then most of the mass goes into the ejecta, and we are left just with a neutron star or a low mass black hole. If the answer is no, then the star undergoes either a failed supernova or just a direct collapse to a black hole, and the final mass of the black hole will be large. And how can we decide if the answer is yes or no? Here is possibly the main issue of this topic, because the answer depends on the complex physics of core collapse supernovae. And in the last few years, the only consensus is about the relationship between this and the final mass and compactness of the progenitor star. If the final mass of the star at the onset of core collapse is very large, then the star has more chances to avoid an explosion and to directly collapse to a black hole, leaving a bigger black hole. But since metal-poor stars, as we have seen here, have also more chances to end their life preserving their mass, then they are also more likely to leave these bigger black holes. And this is what you can see from this plot. This is a model that we published in 2015 of the expected mass of the compact remnant as a function of the zero age-main sequence mass of the progenitor star, the initial mass of the progenitor star, and the different lines are different metallicities from higher to lower. Here you see that the lower the metallicity, the higher the maximum possible mass of the black hole, because of what I just said. And the details depend on the stellar evolution model and on the core collapse supernova prescription that you adopt. And with this kind of model, we can infer some interpretation for the progenitor of LIGO and Virgo black holes under the assumption that they are of stellar origin. For example, we can say that the progenitors of the first event, 150914, should be relatively metal poor. But back in 2015, we neglected several aspects that are quite important. One of them is pair instability. Let me briefly summarize. If a star is very massive and metal poor, in the late evolutionary stages of its life, like at the end of carbon burning, it can efficiently produce gamma ray photons. And when these interact with atomic nuclei, scatter atomic nuclei, this leads to the formation of pairs, electron and positron pairs. This removes pressure, photon pressure, of course, triggering an instability, which is called pair instability. And this develops as a contraction of the stellar core and leads to an increase of the already extreme central stellar temperature that you see here, leading to premature ignition of neon, oxygen, and silicon. And this has, of course, an effect on the final fate and mass of the compact object. Here is again another model of the mass of the compact object versus the ZAMS mass. But here we consider stellar evolution, core collapse supernova, and also a prescription for pair instability. And you can see that there is a range of ZAMS masses for which we expect a zero compact object mass. This is where the instability develops as a peri-instability supernova, and we think that it destroys the star completely, leaving no compact object. And of course, this range depends on the metallicity, is lower for higher metallicity because the central properties of the star depend on metallicity. For lower masses, we still have, from here, instability, but is a pulsational peri-instability. Basically, the star undergoes pulses which enhance the mass loss, and then the star finds a new equilibrium to a lower mass. And in this region, if the star is very massive and metal poor, the gravity is so strong that the instability leads to a direct collapse to a black hole in the intermediate mass black hole regime. And maybe the most interesting feature of accounting for peri-instability is that we expect peri-instability to open a gap in the mass spectrum of compact object between approximately 60 and 120 solar masses. And we have a first problem here, because the primary mass of 190521 is in the middle of this mass gap. So the first obvious question is, how confident are we about the boundaries of the mass gap? There are many uncertainties that come from stellar evolution, massive stellar evolution. And with Guglielmo Costa in this paper, we considered a few of them, like the impact of stellar rotation, the impact of convection, and the onset of the Rejap episodes. The uncertainty on nuclear reaction rates, like the carbon alpha reaction, and the role of the envelope, the final envelope of the star. This plot gives you an idea of two of these ingredients, the fate of the residual envelope of the star and the carbon alpha reaction rate. This is a reaction very important for intermediate mass and massive stars in the late evolutionary stages, but the rate is also very difficult to constrain with observations and in the lab. So here we consider rates between -3 sigma and +3 sigma, which are shown by the different lines. And this is the usual plot of the expected mass of the compact object versus ZAMS mass. But here we fix the metallicity to this value. The difference between the dashed and the solid line is has something to do with the final envelope. The dashed line is the pessimistic case, in which we assume that the star can produce a black hole only if it does not undergo any peri-instability, and that only the final helium core mass participates in the collapse and become part of the black hole. The solid line is the very optimistic case, in which we assume that the entire final residual hydrogen envelope collapses to become part of the black hole. And you see that the impact of the envelope is crucial. With assuming that the envelope collapses, even for a mildly low rate of the carbon alpha, we can produce black holes with mass above 80 solar masses, which are in the 90% credible interval of 190521 primary mass. Does it mean that we can explain binary black hole mergers like 190521 with a single stellar evolution and binary evolution? The situation is even more complex here, because LIGO and Virgo did not observe a single black hole that formed from a single star collapse, which is what we discussed so far. LIGO and Virgo observe binary black hole system where two black holes orbit about each other with a very short initial orbital separation. The binary black hole can merge within a Hubble time only if the initial orbital separation between the two black holes is just a few tenths of solar radii. So how can we produce this very extreme binary system, and what are the implications of the formation channels? In the next few slides, I will focus on two of the most popular formation channels, which are the isolated one and then the dynamical channel. Let's start with the isolated binary formation. The idea is straightforward. We have two massive stars that form already as members of a binary star. They evolve, they leave two black holes, and the two black holes may merge. This is quite natural because we know that massive stars form preferentially in binary or multiple systems. We learned this from the observation. However, the life of a tight binary system is affected by many evolutionary processes that can completely change the final fate of the binary and that make it quite hard to predict, like mass transfer processes or unstable mass transfer, which means common envelope, tides, gravitational wave decay, of course. And so we need to tackle these processes, to study these processes, to understand the features of binary black holes that form from isolated binaries. There are several possible approaches to this problem. In our group, we study it mainly with binary population synthesis. These are codes that are designed to run a large statistical sample of binary stars till they become single or binary compact remnants. So we can run about 1 million binary star per day on a single core. But of course, the code to be so fast, we need to introduce some simplification in the code, like simplifications in the treatment of stellar evolution, which is not on the fly, simplified prescription for core collapse and peristability supernovae, and then we, on top of that, add a formalism for the binary evolution processes I briefly described. In our team, we developed two population synthesis code, MOPSI and 7. You can download them if you want to play with them or use them. You can download them following this link. And I wanted also to show you the smiling faces on some of the main developers of these codes. And with the usage of these codes, in particular the MOPS code, we can obtain information like this one. I will just present this plot about isolated binary evolution because this is, I think, the key one to understand what follows. So this plot shows the total mass of binary black holes that form at the end of our population synthesis simulation. Total mass means mass of black hole 1 plus mass of black hole 2. And here we run 100 million, about 100 million massive binary star simulations with population synthesis, and then we extracted at the end of the simulation the properties of the binary black holes. The different lines are different metallicities from the solar to about 100 solar. The only difference between the top panel and the bottom panel is that in the top panel we show all the binary black holes that form at the end of our simulations, including those with that will never merge within a Hubble time, that have a orbital separation, initial orbital separation, which is too large for gravitational waves to become important. In the bottom panel, we show the subsample of binary black holes that merge within a Hubble time, so the tight systems. And the key difference between the top panel and the bottom panel is the maximum mass. So the top panel, in the top panel, we obtain binary black holes with total mass up to about 130 solar masses, not so different from 1905-21 total mass. In the bottom panel, we see that the maximum mass of binary black hole mergers is only about 85 solar masses. And this difference is an effect of mass transfer and common envelope. In fact, the progenitors of a merging binary black hole should start from a small orbital separation. And this tight binary system undergo during their life mass transfer processes and unstable mass transfer processes, so common envelope, which are highly dissipative processes. They remove most of the final hydrogen envelope from the progenitor stars. So here we only have binary black holes that form without the hydrogen-rich envelope. And you remember from a few slides ago that this leads just to small black holes. Now, the take-home message from this plot and from the single and binary stellar evolution processes that I described is the following. From massive stellar evolution, we have very large uncertainties on the maximum black hole mass. And then we cannot exclude a priori the formation of a black hole with mass larger than 60 solar masses from the collapse of a single star. But this does not mean that we can easily produce a system, an extremely massive system like 1905-21. For essentially two reasons. One, that I mentioned this time for the first time, is the configuration of the spins. Binary evolution processes like mass transfer, like tides, tend to align the spins of the two black holes, as you see on the left in the cartoon, with the orbital angular momentum of the binary black hole. And if in 1905-21 we really see a strong misalignment between the orbital angular momentum and the spins of the two black holes, this is very difficult to reconcile with a isolated binary evolution. Second, and even more serious issue, in my opinion, is that to produce a black hole significantly more massive than 60 solar masses, you need the residual hydrogen envelope to participate to the collapse. But stars in interacting binary system lose all their hydrogen envelope by unstable mass transfer. And then the bottom line is that it's very difficult to produce binary black holes like 1905-21 with isolated binary evolution. And then, of course, we should see whether dynamics can help. Which kind of dynamics? I'm talking about close dynamical encounters between stars and black holes, which can happen only if we have a very high stellar density, approximately higher than 10 to the 3 stars per parsec cube. To give you an idea, in the solar neighbor, the density of stars is about 4 orders of magnitude lower. This density are characteristics of the cores of dense star clusters, like this one in the Large Magellanic Cloud. And what are the processes, the main dynamical processes that can affect the formation and the evolution of binary black holes in star clusters? We know a large number of this kind of processes. I will just mention a couple of examples, starting from the dynamical exchanges, just because I don't want this colloquium to become very long. The dynamical exchanges are a crucial ingredient to produce binary black holes, especially in young dense star cluster. Let's consider this cartoon. In this case, we have a configuration with a black hole and a low mass star. Let's suppose this is a solar mass star. This binary system will not become a binary black hole if it is in isolation, but if it is in the middle of a dense star cluster, it will have chances to interact with other stars and black holes, and a black hole may, interact and kick off the low mass star, producing a new binary black hole. And we think that black holes are efficient in pairing up dynamically in this way because they are among the most massive objects in a stellar cluster, and dynamical exchanges tend to favor the formation of more massive binaries, which are more energetically stable. So not only binary black holes tend to form via dynamical exchanges, but the binary system that form via exchanges have very specific properties. They tend to be more massive than isolated binary black holes, have an initially high eccentricity because of the nature of this interaction, and the dynamical perturbation completely reset any initial memory of the spins. So we expect isotropically oriented spins with non-zero spin components, in most cases with non-zero spin components in the orbital plane of the binary system. So this is the general picture, but now how can we quantify what I just said? One possible approach is to go for direct embodied simulation. So for very accurate simulation where we simulate the interactions between each single star in the star clusters. And in our group, we combine these direct embodied simulations with population synthesis to follow also the evolution of stars and binary stars. And Ugo and Sarah did run so far more than 100,000 young star cluster simulations with a very large initial binary fraction, about 100% for the massive stars. This is consistent with the observations, but is also a bottleneck of this calculation. So this is the first time that we run such a large sample, including a very large initial binary fraction. And I will just show this plot, which is, I think, one of the most representative results that we get from these simulations. It shows the secondary mass versus the primary mass of the binary black hole mergers. The yellow stars here are the LIGO and Virgo black holes after the first part of the third observing run. Everything else is just models. The color markers are binary black hole mergers from our dynamical simulations. Different colors correspond to different metallicities of their progenitors. The field symbols are exchange binary system, binary black holes that exist because they had an exchange, while the unfilled white markers are binary black holes that form from initial binaries, but this were anyway affected by the dynamical evolution of the cluster. And the gray contours, in contrast, are a comparison sample run just with population synthesis, so no dynamics at all in the gray contours. And you can see two main features that distinguish the dynamical formation and the isolated formation. One is apparent if we look down here. Dynamics favors systems with mass ratio significantly lower than 1, which are more difficult to obtain with isolated binary evolution. And so we can kind of naturally explain systems like 190412 and 190814 with dynamics. The second difference is here on the top right. While the isolated binaries reach only up to about 45 solar masses, mass of each black hole in the binary system, for the reason I told you before, the dynamical systems can have masses up to, in this simulation, up to about 90 solar masses. And there are two reasons why these massive mergers happen in our simulation. Between 40 and 60 solar masses, these black holes form from the collapse of a single star, and they form with the collapse of the residual hydrogen envelope. So these are single black holes that in the isolated binary evolution cannot merge with anything else, but in this case pair up via exchange and they merge. But here we have also a few symbols with very large masses. These are too much even for the hydrogen envelope collapse. At least here we do not play with the carbon alpha reaction rate, so it's just a standard rate. What leads to the formation of these objects here, very rare. It is substantially stellar mergers. Dynamics favors not only binary black hole mergers, but also stellar collision stellar mergers. And there is one specific case that is particularly interesting here. If we merge an evolved star with a helium core and a still almost pure hydrogen star, main sequence star, and the collision is not associated with significant mass loss, then we can form a very massive star with an undersized helium core, undersized core with respect to the envelope. And if this star collapses to a black hole before the core grows above the thresholds for pair instability, this can leave a black hole with mass in the gap, which forms without natal kick essentially, and then can stay in the cluster, pair up dynamically with another black hole, and lead to a merger with a mass range not that different from 190521. And now I can explain the plot that I chose as a accompanying plot for this talk. Here you see a merger tree, but it's not the usual merger tree that we see with a galaxy merger tree. This is a stellar merger tree in a simulation by Ugo Di Carlo and collaborators, where we start with 5 main sequence stars, and we have repeated mergers leading to the formation of quite massive black holes. In the end, we have a binary black hole where the 2 black holes have a mass of about 100 solar masses each. Is this the only process that can lead to massive binary black holes in the mass gap or in the intermediate mass regime? No, there are several other possible dynamical mechanisms that lead to the formation of binary black holes. Actually, the most famous one is possibly the so-called hierarchical black hole merger. The idea is simple. If I merge smaller black holes into bigger one, I can produce black holes in the intermediate mass black hole regime. Also in this case, I need a star cluster because the merger remnant is a single black hole, and so it can pair up dynamically only in a star cluster. And the main issue that prevents a substantial growth of the black hole mass with this chain is the relativistic kick. The black hole remnant, the merger product, receives a strong kick at birth because of a relativity effect connected with the asymmetry of the linear momentum emission from gravitational waves. And this kick is of the order of a few hundreds of kilometers per second up to a few thousand, which is way higher than the escape velocity from most star clusters. For sure, it is above the escape velocity of young star clusters, like the one I presented before. But in many cases is above the escape velocity also of the most massive globular clusters and nuclear star clusters, which lie at the center of galaxies. And here we have also a serious computational challenge. If we want to study a nuclear star cluster, we cannot just run a direct embodied simulation, or maybe we can do it just for one simulation, but we cannot probe the parameter space we are interested in. So if we want to simulate many clusters from low mass to high mass, and we want to probe the parameter space, we cannot go for brute force embodied simulation. One alternative approach is to use a semi-analytic model, pretty much the same as a population synthesis model, but including dynamics. And of course, the dynamics that is included is only averaged. It's only a description of the evolution of the semi-major axis and the eccentricity as a result of the dynamical interactions, but averaged over several dynamical interactions. And here in the last few slides, I will show you some result that we can get with this formalism. So here you see a distribution of the masses and spin parameters of binary black hole mergers that we have in nuclear star cluster, adopting our semi-analytic approach, the filled histograms are the first generation binary black hole mergers. The unfilled histograms are the second generation mergers or higher generation. For the spins here, I don't plot the spin magnitudes or directions directly. I plotted the effective spin parameter, Kf, and the precessing spin parameter, Kp. The first one measures essentially how much the spins of the two black holes are aligned with the orbital angular momentum of the binary system. Kp measures instead the component in the orbital plane. And I use these two parameters not because I don't know the magnitudes and orientation, I know them from my model, but because these are the parameters that LIGO and Virgo can measure more easily. We see by looking at the masses that hierarchical mergers can build up very massive black holes in nuclear star cluster up to a few times 10 to the 3 solar masses, but these are very rare. From the spin, we see that there is at least one peculiar feature in Kp, where we have a double horn distribution. From the first generation mergers, we expect relatively low Kp, while from the second generation merger, we expect a larger one. And this feature is there if we assume relatively small spin magnitudes for the first generation. And then we can compare with these models what we get for nuclear star clusters, globular clusters, and young star clusters. So the top panel shows the maximum remnant mass that we obtain from our model, starting from 1 million binary black hole merger per each configuration as a function of the generation number. The different colors correspond to nuclear star clusters, globular clusters, and young star clusters. And we see here that only nuclear star clusters can build up black holes above 1,000 solar masses, and they can do so because they can retain a larger number of generations given their higher escape velocity. In the bottom panel, we see that these very high generation mergers are quite rare, even in nuclear star cluster. This shows the fraction of binary black hole mergers that belong to a given generation divided by all the binary black hole mergers that we have in that population. Nuclear star classes are the more effective ones to produce second generation mergers. About 30% are second generation mergers, but we expect very few black holes in this very large mass regime. And this is the last plot I'm gonna show you. Of course, I'm gonna compare with the observable properties of 190521 that we discussed several times during this talk. Here below you see the secondary mass versus primary mass. Here above the Kf versus Kp. The black contours are the 50 and 90% credible interval from the LIGO and Virgo collaboration, while the 2D histogram, the color map, shows the properties of our binary black hole mergers in the fiducial model for the nuclear star cluster if we consider only generation equal or higher than the second. So here you don't see the first generation. And well, we can produce a system that match not only the masses, but also the values of Kf and especially Kp that we expect from the observations. So I'm nearly done. I just would like to show you this picture, a not so recent picture of my group. We couldn't take a new one because of the coronavirus. And I want to show you this to thank my young collaborators because most of the work I presented here could not have been possible without them. And also I would like to advertise a new postdoctoral fellowship in our team. If you're interested, just contact me, drop me an email. And here are my conclusions. So I try to convince you that there are really many open questions about the formation of black holes from massive stars. And this can deeply affect our knowledge of the mass spectrum of black holes and the mass gap induced by pairing stability. On the other hand, isolated binary black hole mergers seem to be limited to rather low mass, below a total mass of 85, maybe 90 solar masses, while dynamics opens a plethora of new mass ranges and possibilities. So we expect a rich zoology of binary black hole mergers from dynamical channels. And I'd like to thank you for your attention. And now I will be happy to take your questions.
Well, thank you very much, Michela. Let's have a try. This is a really very interesting talk, and I'm fascinated with the sort of amazing predictions you can make. I'm sure we'll have many questions. I'd just like, if I may, all right then, to ask, I think Nadine was the first with the hand, so go ahead, Nadine.
Okay, so I was not first. That's what I wanted to say, but I can ask my question anyway. Thank you, Michela, for this really nice talk. I enjoyed it very much. It's great to see all the progress been made in this field. I had two questions, actually. Maybe they're quick. So for this very peculiar high mass black hole, 190521, so is there anything known about the environment? So do we know whether this is actually sitting at the center of a galaxy or in a dense cluster? Do we know any electromagnetic counterpart for this event?
We are not sure about it, also because the sky map and redshift uncertainty were very large with respect to other detections. This is a 3 detector detection, 3 interferometer detection to noise rate, because it is quite far away at high redshift of about 0.8, and this makes terribly difficult to learn something about the environment. There was claim, very interesting claim, about a possible association with AGN flare. In that case, the environment would be the one of AGN nucleus. That would be, of course, very important to confirm the dynamical formation of these black holes. And it's not the same as I discussed in my slides. So in my slides, I discussed nuclear star cluster, including only the presence of stars of a very dense stellar classes where stars interact with each other and they can trigger these mergers. If this event was happening actually in a AGN disk, also the dense gaseous disk plays a role, because the torques from the gaseous disk can rearrange the orbits of the black holes. They can pair up them efficiently, like the same basically as you do in planet formation simulations. And there is a lot of literature about this, not from my side, not yet, but from especially Barry McKernan, Imre Bartos, Gillian Bellovery, and other people. And I think this is a very interesting scenario that, as I said, increases the zoology of these possible mergers.
Yeah, so this actually was addressing part of my second question, which was if we would include gas accretion into this, because in nuclear star clusters, they sit at the center of galaxies, right? So there is a center of the potential well, they retain gas, and they could in practice also speed up the growth of the black holes and speed up maybe even the merger of the black holes. Is there any way that you can include that in your simulations in the future?
Well, yes, we are already working on that with semi-analytic formalism, because hydrodynamical simulation are simply too much to be coupled with everything. We already have too many things to care about computationally. I would say that from the papers that are already available, the gas accretion is not the main thing that plays a role here. It's more the effect of gas, like gas torques on the dynamics of black holes. Even if there are also a couple of studies about the importance of mass accretion to change, to affect the final mass spectrum of black holes. I think the bottom line of this work, like there is one by Savarzadeh and collaborators, sorry for my poor pronunciation. I think that the bottom line of this work is that gas accretion can be pretty much relevant only if we are in an extremely dense environment, like primordial environment, early universe environment, not at low redshift. And there is also a very interesting work by Lieke van Son and collaborators where they study gas accretion, but from a stellar companion. And they find that is anyway really hard to produce black holes in the per-instability mass gap just with gas accretion, even if you assume that it can be significantly superadded. So yeah, very good question. This has already been studied now and then, and of course these studies do not solve the whole question, but they are an excellent starting point.
Oh, absolutely. Thank you very much. Thank you. Bye.
You're welcome. Bye.
Okay, and we got lots of questions, but during the colloquium, there were a couple that appeared, and I think Hans-Walter Rix had one. So go ahead, Hans-Walter.
Yeah, Michela, thank you very much also for this great talk. I have a question that kind of goes back to your second or third slide, where you showed that kind of world of stellar mass black holes that excites X-ray astronomers and that excites gravitational wave astronomers are quite different regimes, right? So low mass, high mass X-ray binaries and the gravitational wave sources are quite different. You then also talked about that you and your colleagues had developed new binary population synthesis models. And I'm not an expert, but it seemed in the past it was hard to actually build models that could explain both populations. Can you provide me some insight of whether that is still tricky, or do your models also predict sensible things in the regime of low mass and high mass X-ray binaries?
Thanks, and of course, excellent question. Actually, yeah, it is still quite fine-tuning to reproduce all the black holes and neutron star in X-ray binaries that we observe with dynamical mass measurement. I will make just one example. The revised parameters of Cygnus X1 that were recently published with an even more extreme spin than it was known before and more massive black holes. We tried to probe the parameter space for this X-ray binary, and it is almost impossible to produce it, at least based on our simulation set. It is almost impossible to produce it with the stellar wind models that we have at the moment. So you have to relax some assumption in the stellar wind models. I have to say also that X-ray binaries are like a black beast for me, not just for population synthesis, but especially for me, because we don't have information on the luminosity and accretion efficiency of this system directly from population synthesis. To build like a prediction on the luminosities, you have to build an additional model on top of population synthesis. So this makes the parameter space explode and things very difficult to match. Nowadays, we are focusing more on dormant black holes because they at least do not require any additional modeling of the emission properties of the binary system, and hopefully this will be relevant with the forthcoming Gaia observations. So yeah, it is a problem. There is a potential problem with the X-ray binaries for now, and our aim is to go step by step, so to like decompose the problem, start from the simplest system, which are the one where the black hole is, where we don't have an X-ray binary, it's a dormant black hole, and then see if we can get better insight also on the X-ray binaries.
Okay, wonderful. Thank you for filling me in. That all makes sense.
Okay.
Thanks.
We got a couple of minutes before the top of the hour, so I'm going to take the two hands that are up. First of all, Francesco.
He says to go ahead. Sorry, of course. I have a question about the hierarchical mergers. So in order to have this kind of mergers, you need a lot of black holes, a certain number of black holes, of course, which also means a certain number of supernovae explosions. And I wonder, especially in a dense environment, doesn't it increase the chance for a disruption of not only your binary, but I mean, also doesn't it decrease the possibility of the final merger? I mean, did you take into account the fact that the supernova could actually disrupt your system at some point, since you need hierarchical steps in order to make your black hole?
Yeah, thanks for the question. We do include the supernova kick in our population synthesis, and not just the supernova kick itself, but also the Blau kick, which is connected to us with the mass loss, simultaneous mass loss from the system. And I would say the kick is more an issue for the low mass black holes and the neutron star than for these high mass black holes, because to produce these high mass black holes, where high I means more than 20, 25 solar masses, you get them only assuming that supernova fails, is very faint or not at all. So you do not expect a significant kick. So they are not an issue. They are not the main issue for massive black holes. They are definitely crucial to understand the demography of binary neutron star and low mass black holes. And indeed, for those, we have also some comparison between different kick models, how they compare to the main observation that we have, which are the proper motion of young pulsars. I don't know if this answer your question.
Perfectly. Thanks. Very clear.
Thanks.
Okay. Well, I think we've now gone past the top of the hour, so I'm going to sort of call an end to the formal part of the colloquium. Now, there will be an opportunity after we've thanked again Michela for further questions afterwards. But before thanking Michela, I just want to make an announcement about the next colloquia. Now, without any further ado, we will have no colloquium next week, but there will be, the next colloquium will be by Jessica Liu on the 1st of June, also on the topic of searching for black holes in the Milky Way. So let's now open up the video and our audio to thank for this wonderful colloquium. Thank you so much, Michela. Thank you very much indeed.